Do you feel the vibes?
Right. So when we talked about graphing functions, rational functions, and when we talked about vertical asymptotes, we had said that the vertical asymptote is when you set the denominator equal to 0. One thing I did not mention is this is the denominator that does not cancel, right? So this is any denominator that does not cancel. Okay? So let's move over here now. It's any denominator that does not cancel. Okay? Okay. So here, so when you have something in the denominator, when you have a term in the denominator that does cancel, those points give you what we call a point of discontinuity. So when the numerator and the denominator have a common binomial factor, there may be a point of discontinuity. This presents or looks like a hole in the graph, right? But it is called a removable discontinuity. And again, at that point, the function is not defined. So for example, suppose you have y equals 3x plus 6 over x plus 2. Okay? Now, I know that x equals negative 2 is a discontinuity, right? Because at x equals negative 2, the denominator is 0 and the function is undefined. However, when we look at this a little bit more closely, you can factor out a 3 and you get x plus 2 over x plus 2. Now, what happens to this x plus 2? It cancels out. Now, initially we had said x can never equal 2, correct? But now it canceled out. Okay, that means we kind of removed the problem, right? We removed the issue, but still, when you put x equals 2 into the original function, it is undefined. So in that case, x equals negative 2 does not give you a vertical asymptote because it canceled out. Instead, it gives you a removable discontinuity. Okay? All right, let's do an example and you'll know exactly what I'm talking about. So let's take a look at this function and let's graph this. So the first thing you need to do is you have to factor this. Let me actually write it over here. When you factor it, you get x plus 2, x minus 2 over x minus 2. Okay? All right. What happens here is these two get canceled out. So here, f of x is x plus 2, right? So what happened? At the x equals negative 2, what we have is a removable discontinuity at x equals negative 2. But what happened when we canceled? The graph reduced to, or the function reduced to y equals x plus 2, right? What does that look like? What is that? It's just a linear function. It's just a line, right? Are there any asymptotes? No, they went away. Are there any zeros? What would the zeros be? It would just be x equals negative 2, right? Okay, all right. So why don't we graph this now? But, okay, so Oh, I'm sorry. There is a removable discontinuity at x equals positive 2. Okay? So let's graph this function. The 0 is negative 2.
Is that after you remove it?
Okay, why don't we graph this function? So this function is y equals x plus 2. There is a y-intercept over here, up 1 over 1. That's what this is going to look like, right? Now, at x equals positive 2, there is a removable discontinuity. What y value would that correspond to? If I kind of mentally plug negative 2 into this blue function, it would be 4, right? So at x equals 2 and y equals 4 right here, there is a tiny little hole in the graph. So when I graph this function, it looks like this. Okay? So when you graph it, there's a little tiny hole in the graph. All right. Let's do another one. Let's take a look at this one. Okay, so what we're going to do first is factor the numerator, and I get x minus 4, x plus 2, over x minus 3, x plus 2. Okay, Evan. Okay, so take a look at this, all right? When you set the denominator equal to 0, right, x minus 3 and x plus 2, x can't equal 3 and x can't equal negative 2, correct? Now, what happens to this function though? These things cancel, so I have f of x is equal to x minus 4 over x minus 3. Now, I did end up with a denominator. So let's see what we have here. First of all, I have a removable discontinuity at x equals negative 2, right here. Okay, because that canceled. Now, I have a vertical asymptote at x equals 3. Vertical asymptote, x equals 3. You set the denominator equal to 0, right? The horizontal asymptote is y equals what? 1. Okay. What about the 0? The numerator equal to 0, x equals 4. Okay. So let's see. There is a 0 at x equals 4. Horizontal asymptote y equals 1. Vertical asymptote x equals 3. Okay. Now, there is a removable discontinuity at x equals negative 2. Okay, we know that x equals negative 2 is a point where the graph is undefined. So you can never, anywhere, you can never show f of negative 2 because technically the graph is undefined there, right? So we can't really write it down. However, mentally, we're going to try to plug negative 2 into that function just to see the location of that removable discontinuity. Because I know it's at x equals negative 2, right? It's somewhere on this vertical line. But how do I know? Is it here, 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 here? Like, how do I know where it is? So mentally, why don't we plug negative 2 into that function so I get negative 6 over negative 5. That's like 1 over 5, 1 and 1/5, right? So that means the removable discontinuity would be at negative 2 and 1 and 1/5 right there. Okay? All right, so let's plug in another point. Let's plug in, let's say, 0. Okay, when I plug in 0, I get negative 4 over negative 3, 4/3, so that's right there. Okay, so I know that here, this is going to look like this. Right? Don't ever make the line cross into that circle. It has to be a visibly like like a visible circle, but don't ever make the line cross through it. So now I have x equals 4 already. Why don't I plug in x equals 5 and I get 1 over 2. Okay, so that looks like this. Okay, do you see what a beautiful graph that is? Right? Oh, why don't we graph equation A here? So I have x squared minus 4 over x minus 2. Okay, enter. Right, you get this beautiful line, right? The calculator knows to cancel and do this and do that. So I just want to show you, when we draw our graphs, we have to make that removable discontinuity visible, right? So you have to have like a circle or a hole that is visible to the eye. But do you see how it's not visible here? Because in between x equals 1 and x equals 2, it's not just one number. You have an infinite number of numbers there, right? So this removable discontinuity is only at x equals 2. So for example, at x equals 1.999999999, there's a graph. It's only at x equals 2, and then at 2.00001, there's also a graph. So, but we can see this in a couple of ways. So one is, why don't we trace this? Graph trace. So hang on, we're gonna trace. So we're gonna go up to, okay, so it kind of skipped over, right? Okay, so now let's do this. In trace mode, let's type in 2, enter, and you see how it says it's undefined. Okay? Now, if you go to the table, Control T, look, you see that? At 2, it's also undefined.
Blowing my mind.
You didn't tell us about that.
Huh?
You didn't tell us about the trace thing, where you could just find the x value.
Right.
You find the y value with just the x.
Right. There's, okay, so now this is a very, very important piece. Anytime, right, you've got an expression in the denominator of a rational function, whenever that denominator is 0, the graph is undefined. Now, the points where the denominator is 0 are always undefined. They're always out of the domain. And those are the points that are either going to give you your vertical asymptotes or your removable discontinuities. So let me say that again. Any point where the denominator is 0, in this case, it's x equals 2. That point is either going to be a vertical asymptote or a removable discontinuity. If it cancels with the numerator, it's a removable discontinuity. If it doesn't cancel, it's a vertical asymptote. So let's go over here. Any point where the denominator is 0, so x equals 3, x equals negative 2. Any point where the denominator is 0, the graph is undefined there. So each of those points are either going to be a vertical asymptote or a removable discontinuity. So in this case, this x plus 2 canceled out. So this is a removable discontinuity. Get it? Because we removed it. This x equals 3 never canceled out. It's infinitely there, right? So that is a vertical asymptote. And both of those points are points that are out of the domain, and the graph is undefined there. And these things that I just told you are things that you have to take with you to pre-calc and then to calc, and to, because everything is based on what I literally just told you. Okay? Okay.
I'm circling.
Good.
Press start.